Hello and welcome to the FEA tutorial. In this video, we will focus on the parametric study, specifically the optimization. In this demo, we look at the 10 mm straight cantilever bracket, which is made of carbon steel. The vertical surface is mounted on the wall, which will be fixed in the simulation, and on the top surface is subject to a uniform distributed 5 megapascal pressure. The dimension is given in this figure. So the goals of this demo is to find the minimum material used in this bracket and maintain two constraints. The first one is the minimum factor of safety had to be 1.5, and the natural frequency of the bracket is in the range of 260 Hz to 400 Hz. So to run the simulation, we can start the Solidworks software from creating a new part. I select the front plane to create a new sketch. Draw a rectangle. Don't worry about the dimension, and a line here to here, and line to define the triangle holes in the middle. Now I'm going to trim these two lines, get a very rough shape of these brackets. And now we can select these two lines, hold the Control key to select these two lines and make a constraint of parallel. Okay, and define the dimension. The length 175 mm, the height is 100. This is 25. This is 25. The distance is 25. Again, and then apply a filler with 6 mm to the triangle. Okay, so that's the sketch of the bracket. We can go to the feature to extrude this feature to 10 mm thick. Okay, so that's the original design of this bracket. To run the optimization study, we will need to get information from the factor of safety and the natural frequency. So we will need to run two analyses parallel to the optimization. So go to the simulation tab, create a new study, the static, to find the factor of safety. So we just follow the standard procedure of the FEA simulation. Right click the part and then apply the carbon steel, which can be found in the library. Connect the fixture to fix the vertical surface, and then apply the uniform pressure on the top surface, which is 5 megapascal. Then we can run the model. It's very quick to get the simulation result. The maximum we miss it is about 118 megapascal. The yield strength is listed here. Then we can view the factor of safety for this original design based on the remissive stress. Okay. Now we can see from the legend that the minimum factor of safety here is 1.86. Our goal is to maintain the minimum factor of safety 1.5, which means that there's still room to adjust the dimension of this triangle hole. So we can create a new study to find the natural frequency. Again, apply the material from the library and set up the fixed support for the vertical surface. Don't apply the external loads for the natural frequency analysis, otherwise you will consider the initial pressure, initial formation and the initial stress in the natural frequency, which will be not accurate. Can run the model. It takes less than 5 seconds to get the solution. So the information can be found here. The first mode of the frequency is about 330 Hz, which is in the range of 260 to 400. Alright, so we already got the frequency and the factor of safety from the static analysis. Now we can run a optimization study. So right click either from the static or the frequency tab to create a new design study. A new design study tree is here. It's gray, which means that there's no result yet. So we will need to define what's the constraint and what's the goals for this optimization. As we explained a minute ago, we want to adjust the dimension of this hole. So the variable will be the dimension of this distance, the distance from the for the triangle to the three edge of the bracket. So in the variable, we have a drop box to add new new parameters. I give it a name P1, the parameter 1, the value. I will pick up this dimension in the graphics area, the default value 25, and then select the range from 7.5 millimeter to 30 millimeter. And I'm going to add a new parameter, give it a name P2. The value also pick up this value from the graphic area. The default value also 25. That's the original value. In this drop box, select the range again. The minimum value is 7.5 and the maximum is 30. Give another parameters. Give a name P3 and then pick up the last dimension. Okay, and the range will be 10 millimeter to 40 millimeter. And the constraint, there are two constraints, the minimum factor of safety and the natural frequency. So we can add a new sensor. The sensor type will be from the simulation data. The stress here, and we can change to the factor of safety, the minimum model minimum. Okay, so the factor of safety should be no less than 1.5, defined from the static 1 study, and another sensor, which is the frequency. So it's also from the simulation data. Find the frequency in this drop box, Hertz, maximum frequency, and from the mode 1. Okay, so the frequency should be between 260 to 400. And the last bit, we need to define our goal, which is the minimum mesh. So the mesh, and pick up the whole path. In the original design, the value is just below 100 grams. Hit the button OK, and we find the minimum mesh for this study. So everything is ready, then we can run the model. Right, the simulation have finished. We can see that there's a optimum column here. If we select this column, and then we can see the color of the design tree have changed, which means that there's some result we can view. For example, the frequency in this optimum design is about 300 Hz, still in the range of our constraint and the factor of safety. The minimum is about 1.5, and the dimension we can see that from P1 to P3 about 30 mm, 21 and 10 mil. From the result and graph, you can right click and define local trend to see how the parameter affect the result. For example, here I will pick up I will choose P1 parameter 1 in the x-axis, and the constraint to see how the trend of the P1 affect the minimum factor of safety. Choose the optimum result. So with the increase of the P1, the factor of safety also increase. We can define this graph to see how the P2 affect the factor of safety. Again, P2, with the increase of P2, the factor of safety also increase. And how about P3? They are in the same trends. We can have a look at the frequency. In the similar trends, so the increase of the thickness of this bit, because the mass is increased, and then the frequency will drop. In the optimum design, we can get about 19 grams, which is about 10% reduction from the original design.